All right. Thank you everyone for joining us on today's webinar, What's in the Future of 5G Millimeter Wave, sponsored by Qualcomm. My name is Ben Stone and I'm with RCR Wireless News. Our speaker today will be Özge Koyman, Senior Director, Technology, Qualcomm Technologies. After more than a decade of advanced research and development and ecosystem trials, commercial 5G millimeter wave service is now available in more than 55 United States cities and 160 areas in Japan. Looking forward, we expect 5G millimeter wave to expand into new geographic regions across the globe, and new device types and tiers will emerge to take full advantage of millimeter wave's virtually unlimited capacity. As a note, the webinar and the slides will be made available for download after the presentation today. Please be sure to enter any questions that you have for our speaker during the presentation. We will do our best to answer them at the end or follow up after the webinar via email. With that, I'm pleased to give you Özge.
Hello, everyone. Thank you for joining. If some of you joined the talk I had back in November, this will hopefully be a continuation of that, a little bit more in depth. And I'll do my best to go through all the material this time. Last time was a little bit rushed. So today's agenda. Okay, sorry, the slide got stuck a little bit. Today's agenda, I want to start with reviewing some of the past. I think it's good to know where we came from before we talk about what's coming up in the future. So I'll spend about roughly 10 minutes or so just talking about how we got to where we are in NR, especially millimeter wave, and then discuss where we are today in terms of deployments, not only in the US but around the world, and the ecosystem in general. And the smartphones and the CP devices, all the devices out there, and then we'll go to spend roughly 40 minutes on the bulk of the talk on how millimeter wave has evolved or continues to evolve after release 15, so after the initial NR release, and what we have planned for the future. So this is discussing all the updates and improvements we've made in the enhanced mobile broadband, as well as expansion into new verticals like industrial IoT, and then new applications, how we're supporting new applications. So with that, let me get started. So I want to start with just a motivational slide. So this slide is something that I probably covered maybe 6 years ago or so for the first time. Why we actually wanted to go to millimeter wave to begin with, despite all its challenges. As we know, the operators around the world have a capacity issue, and they had a capacity issue 5 years ago. They certainly have more of a capacity issue now, which is why the appeal of millimeter wave was great. So if you look at the 26, 28, 39, 60, all the different bands, we have about 25 times more spectrum there than we do in sub 7. So it's more than just, of course, the capacity play. With the spectrum, we have these large allocations per operator, which has a promise of this multi-gigabit per second data rates, and along with that, lower latency. So the promise was an opportunity for new applications and new use cases in 5G NR. And some of the multi-gigabit per second and some applications we're already seeing in current deployments. So this was really the motivation, but of course it came with a lot of challenges and a lot of skeptics along the way. So I'll address some of those. So what did or what has or what did millimeter wave promise to bring? Of course, there was the rich media and entertainment for outdoor deployments, the enhanced mobile broadband. That was kind of the first target. And there's also the indoor and outdoor aspect of it. Indoor, like venues, stadiums, and transportation hubs, and anywhere where you have a density of users and you want to take advantage of the spatial multiplexing ability, millimeter wave. And then there was the fixed aspect, so the fixed wireless access to the home, to have a fiber-like speeds for home broadband. That was another use case, and that actually has taken off. And then expansion into different verticals like industrial IoT was, always on the horizon as well. And I'll review some of that, some updates on that. And there's some of these that are still yet to come, it's yet to be deployed, and I'll discuss some of those. So just a quick note on, of course, on the way there were a lot of skeptics, and I'll talk about some main aspects where people had concerns. But it was similar to in the 80s, the skeptics on CDMA. CDMA was thought to be too complex, too power hungry, and of course, that was someplace where the skeptics were proven wrong. And I do believe in millimeter wave skeptics are also have been proven wrong. So some of the concerns people had, and that to be honest, we also had as well, but we addressed those challenges. One was that there'd be too limited of a coverage, and it'd be too costly to actually densify and deploy. So we've seen that, with the beam management on both sides and the ability to beamform onto different different objects in space, and to cover all the coverage area, we're able to actually get very good coverage, even just co-sighting in many current deployments. So many current deployments in LTE were on the order of 150 to 200 meter inner sight distance, which looked like it was actually fine. So we didn't really have to densify too much. Another one was that it would only work line of sight, that it'd be susceptible to all kinds of blockage and foliage and rain, and that we showed that with enough diversity in the environment, in the deployment, enough diversity in the phone with multiple antenna modules, and the beam management associated with it, we're able to overcome a lot of this blockage quick enough that we don't lose connectivity, and we were able to have connectivity in line of sight, non-line of sight, block line of sight, whatever you want to call it, fairly good coverage. Another thing was that it was only viable for fixed use. That that it'd be too complex for the phone, and even if it was in the phone, that we wouldn't be able to keep track of all the different objects in space and dynamic blocking, and so mobility wasn't feasible. And that again we showed was wrong, and we overcame that with intelligent beamforming, beam management, and multiple antenna modules. We're actually able to overcome a lot of the issues with mobility and support mobility. And finally, that the RFIC technology was immature, and that it'd be too power hungry, it will have thermal issues and not enough space in the phone. And that again, we showed that we can address all those issues, and we have addressed all those issues. So if any of you have a 5G phone, especially on the Verizon network, you already have multiple antenna modules in there, and you already are using it. And so there's proof in your hand that we've overcome those issues. So I'm a part of Qualcomm R&D. So just quickly show you kind of the steps that we go through. As part of Qualcomm R&D, of course, we look at this, all the challenges and everything early on, from a very open-minded aspect, and part of that is actually prototyping everything that we design, and many of you might have seen our prototypes and demos over the years, and at the same time doing simulations or system simulations along with our engineering services group, who look at deployment as kind of type of simulations. And a lot of our simulations are used to go into standards and make sure that we have a good system design. But it's not just us. We of course partner with and collaborate with all our partners, all the OEMs and infrastructure partners, to make sure that there is an ecosystem. And before we go into these final solutions, these cutting-edge solutions on phones and infrastructure devices that many of you are now using in deployments. So just a few milestones along the way. So actually, tomorrow just coincidentally happens to be my 8th year looking at this. Of course, there's a long history that we leveraged before we focused specifically on this. So there's over a decade of history in the technology, but at least 8 years is when I've been focused specifically on this millimeter wave access. And MWC 2016 is when we had the first demo of a non-line of sight mobile demo, which some of you might have seen. And after that, every year we had some more demos with vehicle and mobility, and then 2018 we had the first NR demos with our partners Ericsson, Nokia, Samsung on the first NR millimeter wave links. And then beyond that, it went into more form factor commercial devices, but we've continued to improve the deployment aspect and making things more robust and coverage better. So every year we've had interesting demos in MWC. So where do deployments stand right now? If you're in the US, you know about Verizon, and you've probably heard about AT&T, so deployments are already happening. If you're in Korea and Japan, deployments are happening this year, so you've probably seen a lot of press on that. But really, it's throughout the world. There are either deployments in all the regions, or they're planned for this year or next year, and that includes China and Europe. And so it's a technology that has really picked up and looks to be, will establish itself in a couple of years in all the regions around the world. And along with that, of course, and I mean, that wouldn't happen without all the OEMs and the partners that are developing all these devices. So there are already a lot of 5G smartphones with millimeter wave, PCs, modules, CP devices, hotspots. So it's a big ecosystem supporting these deployments. So initial deployments have been this outdoor hotspots and outdoor use case, but it is expanding, right? Millimeter wave is expanding, and I shouldn't say it's only outdoor. Verizon has deployed in some stadiums as well. But we will see these deployments expand into indoor enterprises and different types of venues that I mentioned before, the airports and terminals, train terminals, and then expanding into verticals like industrial IoT, which I'll spend some time on later on. One big thing that became very popular actually this past year or so is this fixed wireless access that picked up probably more than people expected. And on that, we did have a recent trial or demo with Ericsson, where we showcased a 6.5 kilometer link with over a gigabit per second connectivity throughput with a high powered CPE device. So this kind of a range and this kind of performance is key to really make this a cost effective and viable fixed wireless access solution. And so this is why it's really picking up around the world. So this is also another exciting thing outside of smartphones. Okay, so that introduction being made, let me go to the bulk of the talk. So I'll spend roughly 38, I guess 40 minutes on this side. So I'll discuss, where we came, what we built up on release 15, all the different releases and what's coming up in the future. And maybe I'll just start with this this timeline. And this is not necessarily millimeter wave specific; it's more 5G NR, 5G specific. But it shows the release 15 foundational release that we had that was focused on mmWave, so enhanced mobile broadband. But it had a lot more. It had a very rich feature set. It had a lot of flexibility to really build upon for the future releases. And in the future releases, release 16, we started adding positioning and some industrial IoT aspects. Release 17 and beyond, we're looking at lower cost devices, NR Lite, new applications like XR, which is the VR and AR, and then taking industrial IoT even further. In addition to improvements in power and beam management for the mmWave use case, and also on the infrastructure side with things like integrated access backhaul for millimeter wave. So it's a constant evolution. So currently we're in release 17. Release 17 will end of this year, and then we'll start release 18. But we are looking much further beyond as well. So let me also go back to the spectrum. Just spend just a little bit of time here, just to make the point that initially the deployments and our focus was 28 gigahertz, 39 gigahertz, and but the design was really not necessarily tied to those bands. So the design is a little bit more generic than that. And then since then we have expanded into new spectrums and continue to expand. So in release 17, we are also looking at 60 gigahertz, which is licensed and unlicensed, depending on what part of the world you are. So different portions are licensed and unlicensed. And then going beyond release 17, there is potential work for even 71 gigahertz and above, so up to 114 gigahertz. Now beyond 114 gigahertz, it's it's that sub-terahertz region, and it's a band that many companies are already looking at, and whether that's a potential 5G band or now it starts slipping into 6G is, it's up for debate. It's probably too early to say. But the point is that there's a lot of spectrum as capacity needs keep continuing to grow. We'll continue to evolve millimeter wave and make sure we can address all these new spectrums if any specific changes have to be made. Okay, so let me start digging into the first topic here. One thing that we always want to make sure is that on the UE side that things, the functionality evolves and that the power, we reduce the power consumption and we improve the robustness and coverage. But a big part of getting these deployments out and making them viable is on the infrastructure side. Right? So we have to make sure that we have enough diversity in the deployments, and so that we can have a robust deployment that has good coverage, coverage similar to what we see in sub-7. And so there's a lot of different technologies you can use for this, a lot of different strategies you can use, which we've looked at, in the past few years. So I have kind of three categories here, three columns. So if you look on the left side, this is a distributed remote radio head. So you can take a GNOP and distribute the remote radio heads throughout the space to create some kind of a diversity, so that in every location you see multiple remote radio heads. And now that distribution can happen through fiber front haul or wireless front haul. So so that could be a good use case for the 70, 80, 90 gigahertz bands. So bands above 71 gigahertz, for instance. In the middle is wireless, so millimeter wave repeaters. So you probably read a lot about repeaters. It's a popular item these days both with established companies as well as startups. Everyone is evaluating it. Everyone is targeting it. So I'm showing two different kinds here. There's on top a simple repeater where you have active or passive repeater. That's just repeating the signal in kind of a single beam way. So it's just kind of a wide beam that it's repeating into. So that itself has some potential use cases. And then below that is the smart repeater. So our smart repeater has some beam management controlled by the GNOP, where it could actually beamform and follow UEs, and has some kind of a TDD awareness. So this, it is starting to come up in 3GPP. So in release 17, we'll start looking at the simple aspect of the simple repeater, and then potentially in release 18, we'll bring in some smart repeater aspects as well. So there's a lot of interest in this from operators. On the right side, we can view integrated access backhaul as really a digital repeater. So this is where we had a first release of this in release 16, and enhancements right now, and then potential more work. So this is really a cell in itself, where the backhaul is coming from a donor GNOP instead of a fiber drop. But it really is a cell in itself and has users that it manages that. So there's access and backhaul in that box. So I'll now just dive into integrated access backhaul, because since that has been a very active topic in 3GPP. So this is really on the way to this disaggregated architecture that's a lot of deployments and operators are looking into these days, where you have the CU-DU split, and there is a GNOP that's connected to the 5G core, and it's a donor for the IAB nodes, and the IAB node itself has a MT terminal, so the MT So mobile terminal that's acts as kind of the UE functionality, and then there's a DU that serves either other IAB nodes or 5G millimeter wave devices. And so it's it can be kind of this wireless deployment. So if I actually illustrate this a little bit further, you'll see that on the left side we have a fiber connected G-Node B with a millimeter wave deployment there, base station there, and that's providing access, of course, to the users, as well as backhaul to all the different IAB nodes that you see. So there's 3 in this example, and those IAB nodes have the capability of being multi-hopped, and then we provide some robustness through redundant links to certain IABs. So it's actually for robustness as well as kind of traffic balancing as well. And so with the combination of this, now you're able to deploy in a coverage area that you want in a more cost-effective way. So what does it actually buy an operator? Why would they want it? Well, if you look on the left side, there are operators, deployments in the world that the inner site distance is not what you would want. So it's not the 150 meter, 200 meter, but it's much more. So on the left, there's an illustration of 3 G-Node Bs that have a fiber drop, but those hexagonals are really where you would want more base stations, more deployments. So you're nowhere close to that density, and it's too cost prohibitive to run fiber to all those locations. So the first step you would take, the middle picture, is to just deploy IAB nodes in all those. So it's wireless backhaul. So you just kind of install it, run power, and that provides you the 5G and our millimeter wave coverage. Now, as time goes by and capacity, so the demand grows and you need more capacity, then slowly you can start running fiber to some of those nodes. And in the extreme on the right side, there's fiber now run to all those IAB nodes. So they've all kind of moved away from the wireless backhaul aspect. So IAB was released in release 16. It was a feature in release 16. In release 17 and beyond, we're adding more features. So release 17, we've added the capability of doing full duplex, so enhanced multiplexing. So being able to simultaneously do the access and backhaul. So receive backhaul from another node and then do access. There's also thoughts in even in release 18 and beyond that to do things like mobile relays, so putting IAB nodes on buses or drones to provide coverage while those vehicles are moving around. Looking into new spectrum, looking at unlicensed, for instance, looking at 60 gigahertz or even above. Enhanced QoS for instance, or industrial IoT, where you have a more latency critical traffic, make sure we can support something like that. There's topology redundancy. So being able to have, 2 parents, again, for reliability and also traffic balancing. So all these are, some of these kind of small subset are in release 17, but, it can continue actually even in release 18 and beyond, given the interest. So there's a lot more room for additional features in IAB. Okay. So I just want to show some simulation results. These were some simulations that we had for this past MWC, so last year's MWC, where we took an area like Frankfurt, where the density and combined with just the topology of the central Frankfurt is not really well suited for co-siting. So we wanted to see how IAB could help if you want to just initially deploy cost effectively. So it's a 1 kilometer squared, and we show that there's only 7 G-Node Bs here, which does actually match your current deployments. And we added up to 28 IAB nodes. So that's I think the high IAB penetration shown on the upper right. And the low is about 13 or 14, so on that order, so about half. So if you look at the bottom, you see that the red is not good, right? So red has poor coverage. So with the existing co-siting, it's really poor coverage in central Frankfurt. But as you add the IAB nodes, you see that the green areas grow quite a bit. So if you look in the upper right, the graphics there, you'll see that the tail end, so the CDF has shifted quite a bit for the tail users and the medium users. So now you get in the dense deployment about 4.5 times more throughput for the tail end, and then it's similar type of improvement for medium. So IAB certainly has a big impact on this type of deployment. Okay, so let me just shift away from IAB a little bit and go a little bit more towards UE type of improvements that we made. Like I said, in release 15 and beyond, we're always making improvements for better reliability, so beam management improvements for reliability and performance. And so this could be multi-beam or multi-panel type of support. So multi-TRP is kind of would be in this, as well as better mobility, and which is shown on the right. So this L1, L2 intercell mobility, that's in release 17. And that's actually an important thing, because what you realize when you start testing mmWave is that the cell boundary is very loosely defined. So if you just turn your back or a truck comes in front of you, then you might suddenly have to switch to hand over to another base station. So if that's happening at a higher layer, then the latency would be too much, and you wouldn't be able to be on the optimal beam as quickly. So trying to reduce that latency and doing this L1, L2 intercell mobility is I think a big deal, and improves performance quite a bit. So on multi-TRP, which is also another important feature, and that was part of release 16 and improved in release 17 as well. We did a simulation of that again in MWC this past year. We again stuck to Frankfurt, and so I just want to show some benefit of multi-TRP. Multi-TRP is really intended for robustness, right? So you're trying to overcome blocking. Blockage is a big problem in mmWave, as many of you know. So here we have 113 G-Node Bs deployed in central Frankfurt with 300 devices. And the best performance we get, throughput performance, is just single TRP with no blocking. So there's no blocking, and the UE is free to talk to the base station. When we had that single TRP, and now suddenly there's a blocking model around it. So we have this randomized blocking model. You see about a 30% drop in the network throughput. When we now enable multi-TRP, so it's the same base stations, it's just we're enabling multi-TRP, so the ability to now receive and transmit from multiple transmission points, then you see that there is an improvement. And that improvement, on the left side you see the improvement, but I would focus more on the right side and see how the improvement helps the tail region, so the low percentile and medium percentile users. And there's a significant improvement there. It goes from 0.3 times to 0.7 times for the tail region. And that's what you're really trying to improve, better performance across all the users. So another area on the UE side is power efficiency. Right? So we always want to improve the power. So that was an effort in of course in all the Gs, for 3G, 4G, and it's an effort here, especially for mmWave. And with that, we've release 16 and release 17 has a number of items on that. So there's an improved wake up radio, so improvements to CDRX, an efficient way of carrier aggregation. So being able to have a kind of a primary carrier and then adding the secondary carriers. So the UE only has to track the primary carriers. There's things in release 17 like control channel PDCCH skipping that provides you a lot of savings. So all these are key to really make sure that we get the power, the battery life that everyone expects. Right? We obviously don't want everything to burn out as soon as you use the system. So along these lines, again, I'll go back to the simulation of Frankfurt, where we showed some of the release 16 power improvements, specifically this wake-up radio improvement, wake-up signal improvement, as well as this enhanced carrier aggregation, where the UE only has to track a primary carrier, and then the other ones get added as secondary carriers. So it's again a 1 kilometer square area with 96 GNOPs this time, but a lot more devices, 1,500 devices. So I'll just kind of point to maybe the final result here instead of going through the details. But if we look at CDRX as the baseline and we add just these two features, then we see that we get an improvement of 53% power reduction for these users. So just adding these two features is a huge difference for power consumption. Okay, so let me now shift to new verticals. So far I've really focused on enhanced mobile broadband and some of the evolution and changes in that. But millimeter wave has, it's more than just that. Right? So we're also expanding into new verticals, specifically industrial IoT. So there are a lot of requirements in industrial IoT that millimeter wave naturally does address. This massive capacity, high throughput, and the isolation from indoor and outdoor. These are mostly inside indoor spaces. And there are other things that maybe is less intuitive, like the ultra low latency or the robustness aspect, because millimeter wave is not seen as a robust system, but actually it can be made very robust, and that's one thing that we've targeted in the past few years. So this is just a video. I don't know if the video is showing that well during this broadcast, but this video is intended to show all the different devices in an industrial space with different, varying, requirements that have to be supported. So some require very low latency, these AGVs and industrial robots. Some are more like enhanced mobile broadband devices, like the tablets and the head-mounted displays. So those are naturally already supported. And then we have a lot of sensors and cameras and those things that, this massive IoT type of devices. So we have to really support all these in an industrial space. On the reliability aspect, obviously you don't want anything to go wrong in an industrial space. So they require this really strict reliability metric. Right? So it's like the 4.9 reliability here. So how do you achieve that in millimeter wave? Well, we've shown actually that similar techniques to what's been done in sub-6, this comp type of techniques or this multi-TRP ways in millimeter wave as well. And so you can actually improve the reliability quite a bit. And in this little illustration, I should also say that if you go into factory space, what we've seen is that things are very predictive in a factory space. It's robot arms moving and conveyor belts moving, and that if the left-hand TRP happens to be blocked, a lot of times the middle or the right TRP is suddenly not blocked because the robot arm moved to block one, but not the other one. So things are very predictive, and so you can make things reliable as long as you have this diversity in transmission points and transmit receive points in the factory space. I think for the sake of time, I'm just going to skip over this a little bit, but these are just some kind of enhancements of comp and multi-TRP, how it applies to industrial IoT. But I do want to make sure I cover all the material coming up. But maybe I'll cover this part. So the industrial IoT, there are improvements that are design improvements. One of them I did mention. So the improvements to beam management. So one thing you want to make sure is that since things are very predictive or can be predictive in the industrial space, that you want to reduce overhead and have some kind of predetermined beam switching. So that's something that we're looking into, and also being able to have this quickly recover from errors, and everything that really brings you to a more reliable operation. So somewhat related to industrial IoT, but not necessarily restricted to industrial IoT, is NR light, and probably that's another counterintuitive thing. Trying to get kind of lower complexity, more power efficient devices in millimeter wave to support things like security cameras or sensors, cheaper low tier phones. I know high-end wearables is listed there, and I don't see that happening in the near future. That's probably more of a sub-6 thing. But for the other categories I listed, there's certainly room for that in millimeter wave, because as the requirements go down, then we can start reducing the complexity as well. So maybe the bandwidths drop. Maybe you're in an industrial space, so your link budget is better, so you don't need as many antennas. Maybe you can afford to have higher latency, and so all these things that we're looking into reduce the complexity enough that make NR light and millimeter wave make sense. And so that's a ongoing effort in release 17 and beyond. So the goal is to actually now support more verticals, right? So make sure that millimeter wave is not just EMBB and now moving into industrial IoT, but there's actually much more more growth for it, right? And as part of that, actually, is also this positioning that's come in. And positioning, it has an industrial IoT aspect, of course, and but it's more than that. It also relates to outdoor, for like here it says the drone tracking and the public safety, and there are a lot of aspects of millimeter wave, the wide bandwidths and the natural beamformed aspect of it that actually plays well into positioning. So as you may know, in release 16, the positioning work started with looser requirements, not centimeter level accuracy, and some of the techniques that are in 3GPP just apply better to millimeter wave, given the beamformed aspect and the wide bandwidths. But in 3GPP, it's kind of a combination of sub-7 as well as millimeter wave. So just to be a little bit more concrete, in release 16, the requirements were more of a meter accuracy, right? So it's indoors 3 meter, outdoor 10 meters, and the types of methods. There was the round trip time, so RTT, angle of arrival, angle of departure, which is well suited for a beamformed system, and then time difference of arrival. And some of these are actually UE controlled, or UE specific, and some are on the infrastructure side. And then there's also things like the single cell positioning, where the angle of arrival and RTT are combined from just a single cell defined positioning. And again, that would be well suited for millimeter wave as well. In release 17, now the requirements are more stringent, because we're looking into IoT in industrial space, where we're into some centimeter level accuracy. So and which requires actually wide bandwidths, and again, well suited for millimeter wave. There's a lower latency positioning, and a higher capacity, being able to support all the different sensors and devices in a factory space, because it's a pretty dense space, which again is well suited for millimeter wave. So these are some of the improvements for positioning that are being thought of for release 17 and beyond. So it's not just release 17. Things like on-demand PRS to reduce the overhead for positioning. So that's an important aspect. On the lower left, the multi-carrier positioning is important. So you want to be able to stitch multiple carriers, the PRS of multiple carriers, to essentially form effectively large bandwidth. So that's to improve your accuracy. So that's another good item. And then for V2X, there's the side link based positioning improvements. And then the upper right, there's the inner band measurements that's also ongoing. So each sub 6 or sub 7 and mmWave have their pros and cons. So to be able to combine them, and because they each react differently in propagation and reflectors, and to combine the measurements and is a good way of eliminating errors, in, especially with non-line of sight links. So those are all ongoing efforts. So side link, which I briefly mentioned in the previous slide, is another area of new area that's obviously it's been there for sub 6 for a while, but now for mmWave as well. And there's many applications for this. One of them that keeps coming up is phone to phone link for gaming. So because you have this high and big high throughput, and you have a low latency, and so it's perfect for in-room gaming. There's also this connectivity to wearables, whether it's XR devices or just watch, or providing a mmWave link to those devices. For high throughput, low latency connectivity. And then there's range extension that always comes up. Providing using the UE as kind of a relay or a multi-hop relay, a mesh. So that's another use case for side link that we're looking into. So all these things that we've that I've mentioned, or especially in release 15, 16, and then going forward to 17 and beyond, we prototype a lot of these features, and make sure that we are constantly proving out that things are improved in terms of power consumption, in terms of performance, robustness, and so many of you have probably seen our MWC demos every year along these lines. So one thing that this is illustrating actually is our last MWC, where we even test. We do maybe kind of more creative things and trying to test, push the limits of our devices and our system design. So this drone that's being shown over here, it's actually not a drone controlled through mmWave, but actually just a phone attached on that drone, and that drone is actually spinning in space and flying as fast as possible in that space, fairly tight space of about 150 meter IST between sites, and we show that the link just doesn't drop. We're trying to stress the beam management on both sides, on our UE as well as the infrastructure. So these test beds, we have an outdoor and an indoor test bed, are key to really proving out different ideas and making sure that they do actually are more than just a simulation and more than just a paper design, but have a real implication for deployments. So just to recap a little bit on, I know we've covered a lot of items here, but I'll just talk a little bit about some of the completed release 16 projects and items, and some of the upcoming release 17 and beyond items, and maybe some of these I haven't covered in this deck. So integrated access backhaul, which we first discussed, is an important thing, and I believe it's important for cost-effective deployments around the world, and that is still in release 17 and potentially has more room for growth. There's this unlicensed IAB and mobile IAB, and so those new features may come in future releases. We always make, of course, improvements in power savings and beam management to improve robustness, and on the UE side for EMBB. And we're looking at spectrum expansion. So I mentioned the 60 gigahertz. Didn't necessarily talk too much in detail about it, but that's an ongoing activity. And that spectrum growth will happen to 71 and above, and potentially even sub-terahertz beyond that. So there'll continue to be new applications and new use cases, new verticals. So industrial IoT is something I talked about, but though there's of course the side link and NR light and millimeter wave will continue to expand into those spaces. There's no reason why it wouldn't. It's well suited for those. And then finally, positioning is like I mentioned, is an important aspect that leverages all the positive aspects of millimeter wave, and that started in Release 16, and it's going to continue, and it's continuing Release 17 and beyond. So one thing that always comes up is 6G. So I'll just kind of end with this. When is 6G coming? And obviously we're into the third release of 5G, and 5G continues to evolve. And I've shown hopefully that there's many ways it can evolve and is evolving. We have multiple more releases coming up, 18, 19, 20 potentially, but historically it's been about 10 years between Gs. So people already are talking about 6G. But I just want to make the point that there's a lot of good ideas in 5G still to really make sure that our initial vision of 5G comes to fruition, and we have deployments across sub-6 and millimeter wave around the world in all the different verticals. So we don't want to lose focus at this point and shift to 6G. So 5G still has a lot of legs, but of course we as other companies are starting to think of 6G and looking at 6G, and what ends up as 6G versus 5G is yet to be determined. Okay, so I think I'm mostly on time, so we have a good amount of time for questions.
Great, thanks, Özge. Great presentation. So yeah, first question. Release 17 will likely open up higher millimeter wave bands, up to 71 gigahertz. So what are the benefits and drawbacks of these new frequencies?
Sure. So Release 17, like I mentioned in the talk, has been looking at 60 gigahertz. And so 60 gigahertz in some parts of the world are all unlicensed. Some parts has licensed and licensed, unlicensed and licensed. So it's kind of a split. And there's some efforts in, trying to have some like regulatory changes to make sure that we can have higher ERPs and some change in 60. But as it stands, 60 with the NR design, as opposed to the 11AD design that's already been in 60 gigahertz, I do believe it actually has the ability to support a lot more use cases, so more than just the in-room use case. That's something that we've shown in simulation and we're testing out right now. And the system design, especially with high ERP, should be able to support EMDB type of use cases, outdoor, indoor, whether it's enterprise deployment or just as almost like another carrier for operators to offload more capacity. So 60 specifically, I think has good potential around the world.
Awesome. And so a question from the audience, aren't the solutions to meet the challenges for millimeter wave entail an expensive device? Is it possible to deploy nationwide network in FR2, given that it's still very spotty, and mid-band will be a better balance? What are your thoughts?
Yeah, so I think even in the early days, this question always came up, right? Because, and I'm not blind to it, so obviously if you want to blanket deploy millimeter wave everywhere in the country, it can be expensive, right? Because the intersite distance has to be fairly small. But I think it's not just millimeter wave only deployment, it's a combination, right? So the mid-band is important to get the full coverage, and the millimeter wave bands are important to offload data and kind of, they complement each other. So a place where, in dense urban areas like New York or Chicago, where you have a lot of capacity need, then you would deploy both, and you would make sure that with a combination of the small cells and repeaters and the IAB nodes and all that combined, you get a good coverage in those areas, so that you're mid-band is not overloaded, because mid-band also will not have all the capacity, will not address all the capacity needs. But you may not have, maybe you're not going to deploy millimeter wave blanket in a small city or in a suburb, right? I'm sure my neighborhood is not going to get it, for instance.
Great. And how should we think about terahertz beyond 100 gigahertz? What new and specialized use cases can this band range address?
Sure. So that's a good question. So so this sub-terahertz and terahertz, I guess anything beyond 100 gigahertz, people have been calling all kinds of different names. In my view, the 100 to maybe 250 is about the sub-terahertz, and the beyond is, let's say, terahertz. So if I look up to 250, there's a lot of spectrum there as well, right? So there's plenty of unlicensed and potentially licensed spectrum, like 145 gigahertz that potentially licensed across the world. And with a lot of spectrum, there's about 7.5, I think, gigahertz at that band. So the propagation characteristics are certainly different. So they're different enough that maybe you won't be able to support the same use cases, right? So their site sizes will be smaller. So maybe now you're talking about ISDs of 20 or at most maybe 50 meters. But again, it's an opportunity for, if it's an eMBB, it's an opportunity for offload more data. So as capacity needs continue to grow, so ability to offload more data. But new uses may also come up, right? So these in-room type of communication, or these point-to-point type of communication, or even front haul or backhaul. Those are all good use cases for these higher bands, I think. So beyond the eMBB. eMBB is probably the more complex and hard to achieve aspect in sub-terahertz, but it's not the only objective.
Awesome. Could you please elaborate on the repeater versus IAB use cases? Is the repeater the cheaper solution, and how IAB is bringing advantages over the repeater?
Yes, so repeater would be the cheaper solution, and it's depending especially on the type of repeater. So some of those repeaters that are in the being tested right now or being sold are these even passive repeaters, right? All they really do is they reflect, essentially just reflectors. But even if they're active, they might be limited with the ERP that they provide. So then as you start adding smarts, maybe it gets closer to IAB. So as you add smarts and you have a TDD awareness, or you have some kind of beam management, then your ERP improves quite a bit, because now you can beamform to users. So that's one advantage. The IAB itself is really just a cell in itself. So it brings, it has its own scheduler. It has, it's kind of a digital repeater, right? So it has, it's hard to say which one is better or worse, actually, depending. It really depends on the particular use case, and if you need capacity or if you just need coverage. And if all you're trying to do is out-the-in coverage, then maybe a simple repeater is good enough. But if you have, many users you're trying to support in a big coverage role, maybe IAB node is the best thing. So it's kind of a cell in itself. So we've done analysis on kind of the whole spectrum from simple repeater all the way to IAB, and they each have their different cost points, but there's no clear-cut answer, I would say, on which one is the optimal solution. So that's why operators are actually looking at all of them, right? All the different solutions.
Great, and sort of similar, but it's good to see a more global adoption of 5G millimeter wave. When do you think repeaters and IAB will have a meaningful impact in accelerating deployments?
Yeah, so I think all those solutions are being tested right now. They're being tested and trialed. And so let's say, okay, on the repeater side, there's a rich history of companies that have done repeaters for 4G. It's a little bit different for millimeter wave repeaters, but again, there are a lot of companies that are addressing it, and actually the startup space is pretty active in this, and they're already working with operators like Verizon. I think you just have to search and you'll see many companies are either selling it already or trialing it heavily. And it's more than Verizon, it's Docomo, in Japan is also working on this. So I think repeaters have made it in to some of these networks and will make it in very shortly because it's already available, like the simple repeaters, not the smart ones. IAB, release 16 completed and release 17 will complete at the end of this year. And I know there are some trials, and I've seen some, you can search and you can find some papers of companies that are working on it. So I would expect products being tested right now will become commercialized at the end of release 17. So that's also something that's coming up. So hopefully within a year, we'll start seeing repeaters and IAB nodes in the networks.
Great. And yeah, we're running up time here. We have a lot of great questions from the audience. So thank you very much. Just to note that we won't be able to get to all of them, but we will do our best to follow up afterwards. So a question from the audience. The main problem with millimeter wave is indoor penetration. How does Qualcomm see that problem getting solved?
Yeah, so indoor penetration, it's it varies from building to building, of course. So in a commercial space, commercial building with modern materials, and maybe actually outside the US specifically, it's very hard to get out to in penetration. So one way of getting the out to in penetration is actually through repeaters. So you can put repeaters in windows to provide coverage for maybe lobbies or certain parts of the office. And if you have what I've been calling the smart repeater that has some kind of beam management, you can actually even go further inside the building to get coverage. Or the other option is to have some kind of a indoor deployment, right? So enterprise type of deployment, to provide full coverage for an office environment or a shopping mall or such. So it's really, I think, it comes down to between those two. But it's very hard to, from a GNOB, to get penetration into a building, just given the characteristics of modern office buildings.
Yeah. And so can you talk about what role AI, ML would play for millimeter wave?
Sure. Yeah, that's a great question. I think I hinted at some of it in the industrial space, where things are very predictive in an industrial space and robot arms moving in predictive, periodic manner. And so that's, and that type of thing actually, even outside, occurs, in indoor deployments or outdoor deployments, whereas there are certain things that are predictive. And so you can actually, you just know that if there's a bus that's coming and it's blocking you, that is just going to continue in that particular direction. So your beam management, can really learn those things and take those things into account. So predictive beam management on the GNOB and the UE side, I think is one place where AI is very important. And then you can, and that's just kind of maybe the more obvious, way of looking at it. And but it plays a role in many other things. Actually, I think in the way you design the code books, and you dynamically change code books, and there's a lot of room for AI in millimeter wave.
Okay, awesome. And a few more questions. So currently, most of operators are commenting on mid or low band 5G. What's your view on the timeline for more momentum of the millimeter wave broader use cases?
So it depends on which region you're looking at. So when the question says most operators are focused or announcing mid to low, maybe that's referring to Europe, where that kind of staging is more common. But in the US, of course, Verizon is the opposite, right? Verizon is talking about millimeter wave, and then other bands maybe will come in. In Japan and Korea, millimeter wave is already deployed with Docomo, Rakuten, and other operators. So it's kind of a region-specific thing, and it's hints to, I guess, the availability of spectrum. But in Europe, even though the focus, maybe is low to mid-tier, millimeter wave is in, fixed wireless access, for instance. So maybe that's the kind of the first focus. Places like Italy, it's very popular, actually, fixed wireless access in millimeter wave. And then from there, it'll go to access, all within the next few years, right? So it's not that far out. So it's just the staging is different in different regions.
Awesome. And I think we have time for one more question. Yeah. So let's just round it out with this one. So, do you think 5G millimeter wave will ever move into lower tier devices, whether it's IoT or smartphones, and how can they be supported efficiently?
Yes, so I think that there is room for that, and I had one slide on that where I discussed the NR light and how things like surveillance cameras or security cameras, and this smart city type of applications, so different sensors throughout the city that have reduced bandwidth requirements or maybe reduce specification, reduce requirements for a number of antennas, and it's feasible. So we're able. I think we can push millimeter wave to lower cost, lower capability devices in certain scenarios. So getting it in something like a watch, right? So wearable is a little bit tougher, and I think that's a better place for mid-band or sub-6 system. But getting it into cameras or those kind of devices, I think there is room for millimeter wave.
Awesome. Great. Well, thanks everyone again for joining us today on this webinar. Thank you so much to our speaker, Ozge, and that concludes our webinar for today.
Okay. Thank you, everyone.